Hello, welcome everyone to our webinar that's offered jointly by the Mobilize Center and Restore Centers at Stanford University. My name is Matt Petrucci. I'm the Scientific Program Manager of both these centers, and I'm excited to serve as your moderator today. Today's speakers are Alison Clouthier and Erin Lee, who will share their methods for integrating bone and joint geometry into musculoskeletal models. The first part of the webinar, Erin Lee will provide an overview of statistical shape modeling and present broad approaches for integrating bone geometry into musculoskeletal models. In the second part of the webinar, Alison Clouthier will lead a tutorial for mapping soft tissue attachment sites across bone shapes generated from a statistical shape model. Today's webinar is brought to you by the Mobilize Center and Restore Centers, which are both supported by the National Institutes of Health. The Mobilize Center is focused on developing and disseminating state-of-the-art biomechanics and machine learning tools for researchers to analyze human movement. The Restore Center is working to make these and other tools for real-world assessment of movement more widely available to the rehab research community. Before we get started, a couple quick reminders about the format of the webinar. We will have a research talk and then a tutorial, and we'd love to take your questions from both. We'll take your questions at the end of the research talk and at the end of the tutorial session. Please type your questions into the Q&A panel in Zoom, not the chat. And one other thing to note, this webinar will be recorded and posted to our YouTube channels. Now I'd like to introduce our speakers for today. Dr. Alison Clouthier is an assistant professor in the School of Human Kinetics at the University of Ottawa. Her research is focused on understanding how patient-specific factors contribute to the risk of musculoskeletal pathology and the success of treatment. She is interested in measuring and simulating knee joint biomechanics to investigate how characteristics such as joint geometry can affect function and contribute to pathology. Dr. Erin Lee is a postdoctoral fellow in kinesiology and health sciences at the University of Waterloo in Ontario, Canada. She completed her PhD in mechanical engineering at Queen's University, where she examined the relationship between shape and function in the shoulder with implications for rotator cuff tear risk. Her CIHR-funded postdoctoral research investigates the interaction among bone shapes, cartilage quality, and joint loading in the progression of knee osteoarthritis. With that, we're excited to have all of you here today. I know we're all excited to hear Alison and Erin speak about their research, so I will let Erin go ahead and begin.
Great. So I just want to thank the Matt and the Mobilize and Restore Centers for having us today. While I get my screen shared and everything.
Looks good.
Great. Okay, so I do want to note that although it's just Allison and I presenting today, we also had a lot of support from Lauren Welty and Anthony Gaddy behind the scenes. And this webinar stemmed from workshops we did as a group at CSB and ISB the last couple summers with Mike Rainbow as well. But today, as Matt mentioned, I'm going to give an overview of how we can integrate bone geometry into musculoskeletal models with statistical shape modeling. And then Allison is going to walk through her study where she developed a morphable model of the knee with an interactive tutorial. And so the reason we care about bone geometry is because we see across many joints that bone shape matters for musculoskeletal disease and injury. So I am a shoulder person, and so I have to start off with an example in the shoulder. But here we're looking at the critical shoulder angle, which is the angle between a line along the glenoid fossa and a line projected to the lateral edge of the acromion. And we see this Goldilocks effect where a larger critical shoulder angle is associated with rotator cuff tears, and a lower critical shoulder angle is associated with glenohumeral arthritis. And then there seems to be this sweet spot in between where a moderate angle is associated with healthy controls. So moving beyond the shoulder and the knee, we see a greater tibial slope angle or a more posteriorly inclined tibial plateau is correlated with a higher incidence of ACL tears. And in the spine, patients with degenerative spondylolisthesis tend to have more posteriorly oriented lumbar facets or more narrow lumbar facet angles compared to healthy controls. And so in a lot of these cases, it is hard to tease out cause from effect or what came first, the disease or the bone shape, but there are some longitudinal studies, such as this one on the right by Nyogi and colleagues, that show that bone shape does in fact predict the onset of disease. And so even though we see these consistent associations between what I'll call at-risk shapes and joint disease and injury, we unfortunately don't have a good grasp on how these bone shapes mechanically contribute to injury risk or disease progression. And so without understanding how these shapes affect the joint mechanically, we can't really design interventions or treatments that account for these at-risk shapes. And so, for example, even if we could screen everybody on this webinar and then identify individuals with bone shapes that are predictive of injury, then what interventions can we prescribe to lower their risk of future injury? Or if a surgeon sees that a patient has a particular bone shape during their surgical planning, how should they then use this information to plan how they're going to orient a joint replacement or reattach a tendon? And so this is the critical gap where we need to understand how bone shape alters joint function before we can inform interventions that effectively prevent or treat disease. And so luckily, models offer an ideal theoretical framework to estimate how bone shape affects joint function because they allow us to isolate changes in shape while controlling other factors like kinematics. And so here I refer to musculoskeletal models quite broadly. So some models, like this artisan's shoulder model on the left, capture muscle geometry and a lot of rich detail, and they give us really realistic lines of action and moment arms. But other models, like many of those based in OpenSim, have more simplified muscle geometry, but allow us to estimate functionally relevant metrics like muscle forces, joint contact forces, and contact pressures. And so we know we care about bone shape, and then we have these great musculoskeletal models to work with. But what do we need to actually integrate bone shape into these musculoskeletal models? And so at the beginning, I provided some examples of clinically relevant shape metrics that are relatively easy to acquire, like the critical shoulder angle here, for example, on this 2D X-ray. However, most of these metrics are 2D and planar, and they only capture a portion of the bone. And so when we're working with these complex 3D musculoskeletal models, it isn't clear how you could then adjust the model's geometry to account for these simple 2D angle changes. And so instead, we want to be able to morph the 3D geometry of the joint. And then once we have this morphable 3D geometry, we can use it to update 3D model features like soft tissue attachment sites, wrapping surfaces, or joint primitives that you use to define your model. And so Allison will spend more time on the second part and go through this in the tutorial part of the webinar. But for now, I'll give an overview of how we can accomplish this first step of morphing 3D geometry using statistical shape models. And so a statistical shape model, or an SSM, is a mathematical representation that captures typical shapes and variations within a class of objects. So in other words, it's a way for us to go from a sample of tens or hundreds or even thousands of individual bone shapes, but then distill it down into fewer shape variables that we can more easily digest and summarize. And so I am going to give a brief overview of the steps you would take to build an SSM, but I'll note that at ISB this past summer, we did a workshop focusing on the shape modeling step. And so if you want more details on these approaches, we do have a set of collab tutorials and slides that you can access with this QR code, and I believe a link in the chat. And so I do want to clarify that I keep referring to bone shape, and I probably will keep referring to bone shape, but this approach of shape modeling can be applied to any structure of interest. So this can include cartilage, meniscus, muscle, or whatever it is that you're interested in capturing the shape of. But I will go through these four main steps of what you need to do to build a shape model. So the first thing you need to do is acquire the 3D geometry from your sample. So you would do this by segmenting 3D imaging data from MRI or CT scans. And then the second step is establishing point-to-point correspondences across all the shapes in your dataset. So when you get a mesh out of your segmenting software, it's going to be comprised of a series of points and connections between them to generate the surface. However, each person's bone is going to be comprised of a different number of points, and those points won't necessarily anatomically correspond to each other. So for example, here, as illustrated in these face silhouettes, each face has a different number of points, and those points don't correspond. So for example, point one is on the forehead in the first person, but on the back of the neck in the second person. So essentially, out of your segmenting software, these vertices will be ordered somewhat randomly. And so to build a shape model, we need all the meshes to have the same number of points, and we need them to anatomically correspond to each other. So here, after correspondence, we see that each face is comprised of the same number of points, and we have anatomical correspondence where point one is the tip of the nose on both points, and point eight is the top of the head, and so forth. And so establishing this node correspondence might be one of the most challenging steps of the process, but there are a lot of packages out there to help with this. Coherent point drift is one of the most widely used algorithms, and it's implemented in Python and MATLAB, and Allison will provide some useful links for that as well later. However, even once we establish this node correspondence, the bones or these sets of points will still vary based on their size, location, and orientation, but we want to isolate only the variation due to shape. So to do that, we need to center all the bones to the same location, scale them all to the same size, and then align them all in the same orientation. And this is all done in a process called Procrustes analysis, which Allison will also include in her tutorial. Um, but what's great about this is now we're only left with the variation in these points due to the variation in shape. And so that's why we call these points now shape coordinates. And so with these shape coordinates, we can then move on to the final step, which is using statistical approaches to get modes of variation in the sample. So this is the step that allows us to go from potentially thousands of shape coordinates that define the bone surface to fewer variables that we care about. So for example, here, I've taken 125 different scapula, then summarized them with a mean shape and two modes of variation. And the utility of this step is that we can generate 3D theoretical shapes and deterministically alter shape along modes of variation that we care about. And so getting these modes of variation can look like a few different things, and this is absolutely not an exhaustive list, but I do want to provide some examples of different ways you can approach getting these 3D shapes of interest. And so first of all, you might want to know what the prevailing modes of variation are in a population. And a common way to do this is with principal components analysis. And this is an unsupervised dimension reduction technique that gives you modes of variation or principal components that explain successively smaller amounts of variation in the dataset. So here I'm showing an example from our lab at the University of Waterloo, where we performed PCA on the femur and tibia of 100 patients with OA. And you can see that each principal component explains less and less variation in shape. And this dimension reduction allows us to plot each individual as a point on this shape space. So each point is an individual's knee, and then where it is defined by their score along the first principal component on the x-axis, and then their score along the second principal component on the y-axis. And you can see that even though we haven't labeled these individuals according to their disease severity or anything, because we did include 100 people with varying degrees of OA severity, we find that the greatest source of variation, or PC1, does appear to show this varying degree of joint degeneration across the sample. And so importantly, this is the approach that Allison used in her paper, and which she'll present next. And in this case, she performed PCA on a set of healthy knees. And what's really cool about this approach is that she looked at modes of variation across the femur, tibia, and patella, their bones and their cartilage, to see how all these structures varied as a single unit across a healthy knee. And so this approach is really nice for exploring underlying shape variation without placing any a priori assumptions on shapes or groups that matter. However, sometimes you do want to directly identify modes of variation that are related to a particular disease or group of interest. And so you could do this a few different ways, but one way is with partial least squares. And this is also a dimension reduction technique that's similar to PCA, but it is supervised. So you provide it with shape, but you also provide it with a response variable of interest. And in this case, for each of our 115 scapula, we labeled them according to whether they had a rotator cuff tear or whether they were a healthy control. And so this is where PLS differs from PCA in that it cares about this response variable, and it provides latent variables that explain successively smaller amounts of covariation across shape and the response variable, so in this case, injury status. So on this shape plot on the right, you can see that these first two latent variables really effectively separate people with tears in orange from healthy controls in teal. And so for this paper, we could then morph scapula shape along a discriminant axis that distinguish the tear group from the control group, and then use these shapes as input for our musculoskeletal model. Another really neat way to do this is with Procrustes ANOVA, which is a multivariate regression approach that doesn't rely on dimension reduction. And so I believe there's a link in the chat to a paper where we use this to find sex differences in scapula shape as well. And so finally, one method I think is really powerful and exciting is that we can also use shape models to generate 3D shapes based on those 2D measures that are relevant and easy to measure in the clinic. So if you recall from the beginning of the presentation, I mentioned that a more narrow lumbar facet angle was associated with degenerative spondylolisthesis. And so here, this is some of Allison's work, where she also used partial least squares, but instead of using a discrete group label, like I did for the scapula, she used the mean facet angle as a continuous response variable. So once again, here on the shape plot, we have our two prevailing latent variables, and then the individuals or the points are colored according to their mean facet angle. And so this allowed her to model how the whole 3D geometry of the lumbar spine changed as the facet angle decreased and became closer to a typical degenerative shape. And so this is really powerful because it allows you to take those 2D measures that are easily accessible and relevant to clinicians, but create 3D morphs that can then be used as input for a model. And so that's just an overview of that last step of finding modes of variation and different approaches that you could take. But I do want to bring this back to the purpose of all of this, which was to understand how specific bone and joint shapes alter joint function so we can better understand their role in disease progression or injury risk. So here now we have this framework where we can move beyond these 2D planar measures to morph the 3D geometry of bone or joint using a statistical shape model. We can then use these morphs to update musculoskeletal model features, and then use this morphed model to examine changes in joint function that might be relevant for disease or injury. So before we move on to knees for the rest of the webinar, I do want to provide an example of how we've done this in the shoulder. So earlier I mentioned this critical shoulder angle of the scapula being associated with an increased risk of rotator cuff tears, with the supraspinatus muscle being the most frequently torn tendon. However, we wanted to see if there were other features across the scapula bone that might be responsible for this supraspinatus degeneration and understand why. So as I described previously, we used partially squares to generate 3D changes in shape that were relevant to rotator cuff injury risk. And so importantly, these shapes did include changes to the critical shoulder angle, but also identified other areas that changed, such as the attachment site of the supraspinatus. And so using these morph shapes, we then modeled the glenohumeral joint and the line of action of the supraspinatus with finite element sheets, and then morphed models to a control-associated model and a tear-associated model. And then finally, we can simulate identical kinematics on both shapes to see how the shape difference affected the supraspinatus. And ultimately, we found that the tear-associated shape shifted the supraspinatus line of action in a way that might inhibit its ability to stabilize the glenohumeral joint and point towards a mechanism of wear and tear over time. And so with that, I am very pleased to turn it over to Allison, who will present her paper, The Effect of Articular Geometry Features Identified Using Statistical Shape Modeling on Knee Biomechanics. And she'll have a collab tutorial to show how to update model features like ligament attachment sites and wrapping services with a statistical shape model. And so I don't want to spoil too much, but I do want to give a quick preview of how cool this work is. So Allison and colleagues examined how morphing the knee changed important aspects of knee mechanics, including cartilage contact pressures, ligament forces, and 6-degree of freedom kinematics. And this slide is showing how morphing the knee along the second principal component changed the lateral trochlear inclination angle. And a shallower angle in blue led to an increase in the predicted medial patellofemoral ligament force, which has implications for patellar instability and dislocation. But stay tuned for far more detail on that from Allison. And so once again, I want to thank Lauren and Anthony for all the support behind the scenes, as well as the Mobilize and Restore groups for having us, as well as the co-authors for the work I presented and my lab group at the University of Waterloo. So I'm happy to take questions on this part of the webinar.
Great. Thanks so much, Erin, for a super clear talk. We'll go ahead and start the Q&A session. So again, if you have questions, please go ahead and type them into the Q&A panel, not the chat, and we'll get to as many as we can before starting the tutorial. We do have one in there from Ranjan Bora, and I believe this came up actually when you were presenting the PCs in the knee from the knee osteoarthritis group, but he was curious what those scores of the PC1 and PC2 may represent in that plot, or do you have an idea of what those modes of variation were?
I can go back.
Okay.
Yes, so, oops, let me slide. Okay. Right. So I guess in terms of what they represent, so the principal components are ordered in terms of how much variation how much variation they explain across the sample. So the first principal component here, because we had a sample of patients with severity ranging from almost no radiographic OA, so a KL score of 0, to very severe radiographic OA, a KL score of 4, the most prevalent mode of variation here was representing the severity of the joint. So if I can play this video, we can see that we see along principal component 1,
Actually,
we're
Erin,
getting osteophytic ridges. Oh,
I
can
think
you
your
see this?
slides are um,
Oh,
maybe try sharing one more time. Yeah, sorry. I think I was shut
oh,
down. Yeah, go
are we
ahead.
back?
Yep, there
Okay.
you go. Yep.
So we can see that principal component 1 is likely capturing this the extent of how much they varied in their severity of disease. So
Mm,
we can see the colors are showing where the greatest movement is happening in the bone. So we can
yeah.
see around the articular surface, the surfaces are flattening, and then we're getting that osteophytic ridging around the articular surfaces. So this is probably a sign of that degeneration. And then it looked like in principal component two, I don't have it here, but the next thing appeared to be a change in how narrow the shaft is, which might represent variation between males and females, and other underlying sources of variation. So definitely more to dig into here.
Yeah. And
Thanks
it's
for that
cool that
question.
you see even like with Allison's model too, then it's like there's a difference in what the top modes of variation are and what they relate to. So yeah.
Mhm.
Look, so we got a few more. Next question is from Brooklyn Vargas. What are some difficulties you have encountered with introducing these morphological differences into models, and how do you work through them?
So would that be in when we're working with the musculoskeletal model itself, probably?
Probably, yeah. Yeah, for an example, yeah.
Okay, well, I think maybe Allison will have more to jump on here because she's done so much of this in the knee. In the shoulder, we'll say the examples I provided, we kept it to the rotator cuff muscles, partially because I'm gonna go a little bit further. Kept it to the rotator cuff muscles partially because we were looking at shape changes across the scapula. We wanted to
Mhm.
see how changes in those attachment sites affected those muscles. However, if I then wanted to extend this to a morphable model of the entire shoulder, then we'd also want to look at changes that are also occurring across the humerus, across the torso, because we have so many muscles that cross over multiple bones. So for me, that would be one thing. I will say also for the shoulder, just getting the shape model to work in the first place is challenging because getting an anatomical correspondence across the scapula can be very, very difficult. And so those are some things we ran into. But there may be a good follow-up will be after Allison goes through the tutorial on how to actually morph aspects of the model.
Yeah, certainly. And this kind of relates actually to the next question was actually what we were just discussing about the PCs, but Firas Bakluti uh, was asking if we create a statistical shape model of healthy shoulders and diseased shoulders separately, would the PCs be different in variation? And I guess how would you deal with that in terms of analysis?
I would absolutely anticipate the modes of variation would be different. So
Hmm.
I think it all comes down to what question you're trying to answer. So I would imagine, just like what we have with the patients with knee OA, if you look at only the diseased group, you might expect more of a range in shape representing the disease severity. Whereas across a healthy population, it might be more things that represent, for example, differences we see because of sex differences, differences because of height differences, other underlying sources of variation. So I think it does depend on your question, and how you want to define that sample.
Definitely. Um, let's see. The next question is from Subramaniam Murumala. Um, and this may actually relate to the tutorial a little bit too, Allison, when we get to like kinematic changes. So feel free to jump in here. But what basically the question is, what could be the quantum of changes in kinematics before and after considering the 3D model or the 3D shape change? So if you do account for it and don't account for it, do you see large kinematic differences?
So and that'll be really nice with the framework Allison used because they provided gross kinematics for the walking model, but then allowed some of the finer tuned kinematics to change according to the geometry. So she'll provide some examples of how that changed. This is a good question. And in this study for the shoulder, we found that what separated most the group with tears from the group without tears was the glenoid version. So whether the glenoid was oriented anterior and posterior. And the difference in the groups between the mean shapes was about 8 degrees. And so that led to a fairly large change in our lines of action of the muscles. And then so we did do a kinematic simulation after to see if we perturbed the kinematics, how much do we have to perturb the kinematics to get the function to look the same again? So how much do we have to change the kinematics to modulate the change in shape? And it ended up being about 10 degrees in one plane and 10 degrees in another plane. So it was actually quite a large kinematic difference to account for the difference in shape. I hope that answers your question.
Definitely. May just take one more before we start with Allison's tutorial. This is from Tice Marquez. After you get your mean shape and standard deviation changes in bone shape across the varying modes, how do you verify the point correspondence is of high quality and not distorting the mesh that is not capturing like true shape changes? Or yeah, how do you find that balance between point correspondence and actual shape change?
That's a really great question because it's definitely a challenging aspect. So the first is you would want to see if your corresponding shape well represents your original shape. So you could do this by overlaying your original shape and then the shape you have after correspondence. And you could use something like a surface to surface error and look across the whole bone to see is
Mm,
your corresponding bone still capturing the geometry well? The next thing is even if the geometry is well captured, you could still have errors and the corresponding bones might shift around the edge. So in the example of the faces, we might find that even though you're still capturing the tip of the nose, for example, point one might have slid off the side or something. And
mm,
so in that case, you could use visualizations like changing the mesh by color throughout to see if the the nodes from the original mesh still anatomically correspond to your corresponding mesh. And Allison does go through where she's checked this node correspondence in her tutorial as an example as well. But yes, that's a really important step to make sure that your shape model is not just capturing error in your correspondence method.